In this lecture, we are going to study the chapter A, Atoms and Periodic Table. Please complete the Atomic Spectral Lab and start working on Appendix J and the homework number 8. Also, please complete the Special Lab report, Simple Pendulum, length variation on April 3. Today we know the atoms are not individual units, but are made of even smaller particles. In this picture we had a real image of the atoms of copper. And we can see today we are able to see the atoms, even if we are not able to see the protons, neutrons, or electrons, but we are able to see the atoms. And the technique was used to obtain this image is transmission electron microscopy. And we can see the scale for this image is 5 nanometers. Then the scale 1 nanometers, remember, is 10 to the power minus 9 meter. Yes, it's really a small is a small length. Yes, it's a small length. Then here we had 1 nanometer, and we had about 5 atoms in 1 nanometer. Yes, and today we are able to see the atoms. Again, this is a real picture of the copper atoms. Then the question is how it is possible that scientists can tell us about the part of something so small that it cannot be seen. Yes, how the scientists can talking about the electrons, protons, or neutrons if we cannot see that particles. Then the answer is that these things cannot be observed directly, but their existence can be inferred from experimental evidence. Then the experiments help to the scientists to discover the electrons, to discover the protons and the neutrons, and any other some additional particles that is called subparticles of the atoms. In this image, we had the atomic model, the evolution of the atomic model through the time, and we can see the last 200 years was really the important evolution of the atomic model, even though the idea of the atoms was proposed by Democritus about 2,500 years ago. And let's describe the next slide. We are going to describe briefly the story about the evolution of the atomic model. The concept of atom is very old, is dating back to ancient Greek philosophers about 2,500 years ago. And Democritus, he proposed in 460 before Christ, he proposed the matter could not be divided indefinitely. What does it mean is, for example, if you had a piece of rock, you can divide in a small piece, but if there is some point you cannot divide anymore this, you cannot divide anymore this the rock, and that small particle you cannot divide is he called that particle atom. Then also he proposed that the matter is discontinuous or made up of individual particles. And also he was the first person that used the word atom, that means indivisible or unconquerable. But at this time also was Aristotle. He contrasted the Democritus the Democritus idea about the atom. Then what Aristotle he proposes, everything was made by 4 elements, like earth, fire, air, and water. And the problem was most people believe Aristotle over Democritus for about 2000 years. Then in 1800, John Dalton, he was a chemist, and he was studying the chemical reaction. Then in order to explain what he found when he studied the chemical reaction, he introduced atomic theory to explain his results. Then he claimed 5 postulates that make up the atomic theory. The first postulate was all matter is made of atoms, and atoms are indivisible and indestructible. An element is made up of identical atoms. Means if you have a piece of gold, then all the atoms of this piece are identical. Yes? That now maybe is easier to understand, but not at this time. Different elements had atoms with different masses. Yes? Then the mass of the elements that belong to the piece of gold has some mass, but the mass of the elements that conform the piece of iron has different mass. Yes? Chemical compounds are made of atoms in specific integer ratios. I mean, if, for example, if we had water, then we had 2 hydrogens and 1 oxygen. It's some specific integer ratio. The atoms are neither created or destroyed in chemical reactions. And he proposed this model is called the ball model. Then he proposed like the atoms are like balls and without any subparticle. Then after 100 years, J.J. Thomson, he was a physicist from England, and he discovered the electron. He won the Nobel Prize because of this work. Then he did the cathode ray experiment, and what he did in this experiment is he took a empty tube, yes, and he put some metal plates here, and he applied some voltage. Then one was positive pole, and the other was the negative pole, the other was the positive pole. Then when he applied the voltage, what he observed was some ray coming from the negative cathode to positive or to the anode. He observed some ray travel from cathode to anode. Then he was curious about this ray. Then he was trying to understand what was the composition of this ray. Then he placed two plates close to the tube, and what he observed was the ray was bent toward the positive plate. Then, because he knows this was a positive plate, and the only way this ray was attracted by the positive plate if the ray is made up of the negative charge. And he say then this ray was a negative charge. And if this ray is a negative charge, it's because the atoms belong to this, the atoms that conform this plate is also that atoms have also negative charge, and now we know are electrons. Then also he slide an iron and magnet. He slide a magnet close to the tube, and he observed also some deviation of the ray. Then he took some measurements about the voltage, the magnetic and electric forces, and he was able to combine this result. He was able to calculate the charge to mass ratio of the electron. Then he was able to obtain this value. The charge of the electron divided by the mass of the electron equals to 1.76 10 to the power 8 coulomb per gram. Then he was not able to calculate these values, but he was able to calculate the ratio. Then with this experiment, what he discovered was the atom must have some negative charge, and this charge he identified as the electron. And because of this study, he won the Nobel Prize. In his model, which is called the plum-pudding model, it looks like that. There is a mass, there is a positive charge, and in this positive charge, the negative charge is embedded. Like here, the raisins, you can see this represent the negative charge which embed into the positive charge. Then the model looks like that. Yes. Now the model is not just a ball, it's just we have the ball, which is a positive charge, and inside of this positive charge is embedded the negative charge. Here is a real picture of this experiment, and we can see here the ray and how the ray is deviate when the magnet is close to the tube. In the next experiment was conducted by Robert A. Millikan, and he was able to calculate the charge of the electron. And he did the drop oil experiment. Then what he did is, it's just 2 years after J.J. Thomson he conducted this experiment. Then this is a real chamber he used for his experiment. He used for the experiment, and here inside of the chamber he put 2 plates, one positive plate, the other is negative plate, and he applied some voltage through this applied a voltage to these plates. And at the same time, he dropped inside using the sprayer. He put inside some oil drops, and he was able to see the drops using the viewing scope. He was able to see the drops inside of the chamber. Then what he observed was when he applied the voltage, depending on how much voltage, sometimes the drops move up, sometimes the drops move up. Then here he applied, let's see, here he has 0 volts, 2, 3, 4, 5, 6, 7, 8, 9. Then what 10 here, let me go here, 10. Then these numbers are per 1,000 volts. And what happened is when he apply high voltage like 10,000 volts, yes, here is each of this number is per 1,000, it's multiplied by 1,000. And when he applied about 10,000 drops, the 10,000 volts, the drops move up. Yes. And the reason is the electrical force was larger than gravity force. Then the drop moves up. What happened if the voltage was less than 3,000 volts? Yes, in this part it was here was less than 3,000. The drops move down. Yes, that drop moves down, and the reason is, in this case, the gravity force was larger than electrical force. Then the gravity force is the magnitude of the gravity force is larger, then pull the oil drop down. Then what he found was at about 3,000, yes, in this voltage, the drop was stay still, and the drop he was able to to get the same, at this voltage, the electrical force was equal to the gravity force. Then what he found is in about 3000 volts, when the voltage was about 3000, the electrical force equal to the gravity force. Then the drop was stay still, yes, like is in this picture. Yes. Then using this, when he was able to see that, then he was able to measure the radius of the drop, and using the density he was able to calculate the mass of the drop. Then what he did, he calculated the mass of the drop. He was able also, let's write here the units, probably kilograms, we can write here. Then he applied some voltage and he generated different kind, small drops, big drops. And what he observed was when he was able to calculate the charge for each volt, yes, because he used this, he knows the electrical force equals to the gravity force. Then using this equation, he was able to calculate the charge. We are not going to discuss these details, but what I am going to discuss is the results. Then using this information, yes, and he knows the mass, he knows the voltage, he was able to calculate the charge for each drop. And what he found is the values he got for the different charge was something like that. He got one, for example, this is 1.6 10 to the power minus 19 coulomb. For other drops, he got like 3.2 minus 19 coulomb. For other drops, he got, for example, 4.8 6.4 10 to the power minus 19 coulomb. Then this is some example, the charge he got for the oil drops, and what he observed is in always the values of the charge he got for the different drops was always multiple of 1.6. As 1.6 times 2 is 3.2. This is 1. I want just to make sure this is 1. Was 3.2, 1.6 times 3 is 4.8, 1.6 times 4 is 6.4. Then always the charge was multiples of 1.6 10 to the power minus 19. And also the minimum charge he got was 1.6 10 to the power minus 19. Then what was his conclusion? Is he concluded this is the charge of the electron. This is the charge. This is the fundamental charge. This is the charge of the electron. And all the charges will be multiples of that number. Then using this through this experiment, he was able to calculate the charge of the electron. He was able to find the charge of the electron. Also using the charge mass ratio found by J.J. Thomson, he was able also to calculate the mass of the electron. Then he found this one through his experiment, as the charge of the electron. But J.J. Thomson, he calculated this ratio, then combined these two results, he was able to calculate the mass of the electron. Then now we will see what Ernest Rutherford did, and he discovered the atomic nucleus. He discovered the nucleus of the electron. Then what he did is, what was his experiment? Is the gold foil experiment. Then he he just he took some ultra thin gold foil like that. It's really thin gold foil, and then he hit this aluminum foil with alpha particles. Alpha particles are positive particles. And what he observed, and also he put some fluorescent screen here in order to see the results. Then what he observed is when the alpha particles was hit this ultra thin gold foil, is most of the alpha particles pass and hit the fluorescent screen. There's most of the particles pass through the gold foil without deflected, but few of them was deflected at larger angles. Just few of the alpha particles was deflected to the largest angle, as is shown here in the image. Then when he analyzed this result, what was his conclusions? The first thing is, he said most of the alpha particles, the alpha ray pass through the, as we can see here, this is the gold atoms, and most of the ray passed through this one, but few of them was scattered. It's like this one, probably this one was scattered to higher angles. Then he said the only way that happened, because we had the alpha particles and positive particles, the only way this repelled, yes, was repelled by something, that something must be also positive, yes, because remember, only light charges repel. And he said something positive must be inside of the atom. Yes, there is some concentration of positive mass inside of the atoms. It's the only way we can explain this result. Then, what was his conclusion after the experiment? First, the atom is mostly empty space. Also, he concluded there is a massive positive charge in the atom. Also, the electrons orbit the nucleus but are not part of it. And finally, the gold foil experiment led him to discover the nucleus, as the massive positive charge in the atoms was the nucleus. Then later, also the protons were discovered and the neutrons also was discovered as later. Then this was the Rutherford atoms model, and he proposed there is a positive massive charge in the middle of the atoms, and around this one there is the electrons orbit around this positive the positive charge mass. Yes, there is the electrons orbit around this positive charge, which is called nucleus. In 1912, Niels Bohr, he developed the planetary model of the atom. And what he did, he combined the results obtained from different scientists, and he incorporated the quantum concept of Planck and Albert Einstein with the Rutherford model. And he took these three results and he combined to propose his theory. And in remember that in 1900, Max Planck, he introduced the idea that matter emits and absorbs energy in discrete units called quanta. And in 1995, Albert Einstein, he extended the quantum concept to include light, and that light consists of discrete units called photons. And remember, we studied these two ideas in the photoelectric experiment. Then the energy of photon is directly proportional to the frequency of vibration. Then remember, we can calculate the energy if we multiply the Planck constant times the frequency. And what he proposed was this model. And he said the orbits, the electrons can be just in some particular orbits. It's not any orbit. The electron can stay in some particular orbit. When we say orbit, it's related to some particular energy. So some particular energy. Then the electrons only exist in certain allowed orbits. It's not in any orbit as Rutherford say in his model. And this was the first conclusion when he combined all these experimental results. Then he concluded the first thing was the electron only exists in certain allowed orbits. Yes, like this orbit and this orbit. And again, when we say orbit, it's related to some energy. Then radiation is emitted or absorbed when changing orbits. Then the atom or the element can emit or absorb radiation when change the orbit. Then if the electron can jump from this orbit to this orbit, then that electron can emit some radiation. But within an orbit, the electron doesn't radiate. Then if the energy is not enough to jump from here to here, the electron, that material is not going to radiate some energy. Then can radiate only if the electron can move from orbit to orbit. Then what also he combined the equation found by Albert Einstein, and he also applied this equation to the atomic model he proposed. Then he said the energy of the photon is exactly equal to the difference in the energy level of the two orbits. Then that radiation, remember, if the electron can jump from one orbit to another orbit, will emit some radiation. Then that radiation has some energy, some frequency, and some wavelength, yes, because this is we studied in the last chapter. Then the energy of that radiation equals to the difference between the energy of the higher level minus the energy of the lower level of the energy of the orbits. And if we combine this with the Albert Einstein equation, then this energy, the difference between the energy of these two orbits must equal to the constant Planck times the frequency. Remember, energy equals to h multiplied by frequency. Then based on this theory, then another two scientists, theoretician scientists, also he developed some mathematical model to explain the motion of the electron in the orbits. And according to his, when he developed his mathematical model, what he found is the only way they can explain his result. The only way he can explain the results he got when he developed that mathematical model, if the orbits, yes, that propose Niels Bohr was not just one orbit, that orbit or shells that has some subshell, some suborbit. Then he proposed the first orbit, yes, the first orbit has one subshell. But the second orbit has two subshells of energy, and the third orbit has three subshells of three suborbits. Yes. Then Schrödinger, yes, Erwin Schrödinger, he developed a mathematical model that proposed that the atom was arranged as layers within layers in terms of the electron shells. Yes, layers within layers. And later, Heisenberg, he proposed another model, and he say is according to his calculation, to his model, mathematical model he developed, he proposed that it is not possible to measure the momentum, means the velocity. Remember, momentum is mass times velocity. It's not possible to measure the momentum and the position of the electron at the same time. What we can measure is just the probability that the electron will be found in a certain region, and he called that region the orbit. And you can see here is he proposed this model is the electron can be in any of these places, but the higher probability where we can find the electron is in this orbit. But there is a probability that electron can be in any of these, in any other place. Then finally here we had the evolution, and just we mentioned few experiments that contribute to the development of the atomic model that we have right now. And just I want to discuss again this one, to review this one again, because the next thing we are going to explain is based on the Niels Bohr result. And remember is when the electron jump or move from one orbit to another orbit, radiates some particular energy at some particular value of energy. That radiation has some particular value of energy, and we can calculate the frequency of that radiation if we know the difference between the energy of the two orbits. Then we can calculate the frequency of that radiation, and if we know the frequency of the radiation, we can calculate also the wavelength of that radiation. That what happens if that radiation is in the visible range, then we are able to see that radiation. For example, if the radiation that element can emit is red, then we can see that radiation. If it's green, we can see that radiation is yellow. If it's blue, is violet, then we can see that radiation. If that radiation is infrared or ultraviolet, we cannot see that radiation. And in your experiment, yes, in the experiment you are going to complete, then is based on this, on what we are going to explain in the next slide. And just remember this concept. Then we are going now to study, based on that theory, we are going to study the atomic spectrum. Then what happened if the white light is passed through the slit and then passed through the prism, is we will see all the colors that constitute the white light. Yes. Then if we are able to disperse the white light, we can see all the colors. Yes. We can see all the visible spectrum. And what we will see, if we are able to see, if we can disperse the light, what we will see is the continuum spectrum, we are going to see all the reds, all the yellows, all the greens, the blue, and the violets colors, something like that. Then in case of the white light, remember that colors are energy. Yes, energy, frequency, or wavelength. Yes, we can describe the colors are waves, and we can describe that waves using even the energy, frequency, and the wavelength. Then the energy of the wavelength is over a continuous range. Yes, this is happening in case of the white light. Now, what happens if we give enough energy to some element like hydrogen, helium, and they can emit light? Then, and what were the colors they can emit? Yes. Then in this, we are going to study what is the light from incandescent gas. How we can get that incandescent gas? Then here we had a tube, and inside of the tube we had some gas. For example, hydrogen. Yes, can be helium, can be mercury, or can be even also a compound like carbon dioxide, for example. Now, if we apply high voltage to this tube, then the electrons inside is going to excite it. They will get energy. They start moving from one orbit to another orbit. They start jump from one orbit to another orbit. And also they can go back, yes, trying to get lower energy. They can go back to the original orbit. Then that happens. When we apply high voltage, then the gas inside of the tube is going to ionize and is going to emit some light. And here is a few examples what happened when we apply high voltage to some this is called discharge tube, or this kind of tube. For example, we had helium here, we had neon, we had argon, we had krypton, we had xenon. Here is the light they emit when we apply high voltage. Then now we can do exactly the same we did with the white light. Yes, we pass this light to the slip, then to disperse that light, then we can pass this light through the prism. And we can do the same thing if we observe this light using the spectrometer. Then we will see the same. Then what happens is when we disperse the light coming from this tube, then we can see some particular colors, some particular radiation. It's not like the white light, we can see the continuous. We see some particular lines, and these lines correspond to the energy is emitted by the electrons when they move from one orbit to another orbit. In this case, if we had hydrogen, these are the colors, these are the radiations is allowed for the electrons in the orbit. Then if we had elements and molecules, the excited atoms radiate energy. Yes, when we apply high voltage, we get energy to that atoms, and then the electrons, we get enough energy to the atoms, and the electron can jump from one level of energy to another level of energy. But this energy is not over continuous range. Yes, it's not like this case. It's just some particular values of energy, means some particular colors. That means the energy is emitted in a discrete quantized energies. Yes, in some particular values of energy. And this spectra, these colors that is emitted by some particular element or some particular compound, is called the line spectra. then this, each element, each component has some particular line spectra. It's like a fingerprint. Yes? You can identify that material using the line spectra, because the hydrogen will be emit always this, will be had always this line spectra. And there's two different kind of line spectra. One is the emission and the other is the absorption. Yes? And in our experiment, we will see the emission spectra. Let me move to the next. Here we had some emission line spectrum for some elements, and this is for mercury. Then mercury always will have this kind of this line spectrum. This is for nitrogen, neon, and hydrogen. More electrons, more complex is the line spectrum. Then the light from incandescent gas produce a line spectrum as atoms emit certain frequencies that are characteristic of each element. Yes. Then emit some radiations that are particular for this element. Yes, for that element. Yes. And this always is the lines for mercury. These are the lines for nitrogen, for neon, and this is for hydrogen. Then what we will do in the next slide is we are going to study what is the physics, what is the math behind of these colors, and we will do that SCI just for hydrogen, because hydrogen has just one electron and it's easier the analysis. For more electron, more complex is the analysis. Then what we will do is we will try to find what is the math, what is the equations behind of this color, how we can find mathematically the line spectrum for hydrogen must be violet, must be blue, and must be red. Then let's do that part. Then what we are going to use the Born's theory to try to find mathematically the hydrogen's emission lines. And what we had here, you see, these are the level of energy. This is 1, 2, 3, 4, 5, 6. These are is N means are the energy levels. Yes, I want just maybe show here. This is the nucleus, and this is N equal 1. Yes, this is represented by this one. N equal 2. Then this 2 is represented by this 2. And this value is here is the energy that corresponds to this orbit. Yes. This value is right here is the energy that corresponds to this. And if we had another orbit, will be the third one. This is the energy that corresponds to this orbit. And these values are the energy for this particular orbit. Also here we had the same value of energy in electron volts. And in some cases it's convenient because you don't have this exponent part here. The numbers are easier. And to convert from electron volts to joules, you can use this conversion factor. But in our case, we will use the energy in joules because the constant, the max plus constant we are using in our problems is joules per second. Then in our problems, we will use these values of energy, the energy in joules. Then now we had this equation. Is what happened is usually in our problems we had the value of the energy of the first, or it's called also the fundamental the lowest orbit is n equal 1. Then if we know this value, we are able to calculate the energy for any other orbit just using this equation. This is the energy correspond to the n equal 1, means this value, and n2, this n correspond to the orbit. Yes? If you want to find for the second orbit, then you had to divide this number by 2 to the power 2, means you had to divide this number by 4. We will do some problem applying this equation. Then here the thing is, this equation allows you to calculate the energy for any orbit. Yes, just you need to divide by n to the second power. Yes, if it's in the second, you divide by 4. Is for the third, you divide by 9, because third to the second is 9. Is the 4, you need to divide by 16. Once you know the energy for each orbit, then you can calculate the difference between the energy of the orbit where the atom move. Yes, for example, if the atom moves from the orbit number 6 to orbit number 2, then we need to subtract this energy minus this energy. If the electron moves from the orbit number 5 to orbit number 2, we need to subtract this value minus this value. And the same happens with this. Yes. And this is the difference between the energy of two orbits, where the electron moves, between what energies the electron move. But we know by the equation of Albert Einstein, this difference equals to the Planck constant times the frequency. And if we know this one, and we know this one because it's a constant, we can calculate the frequency of the radiation is emitted by the electron or the atom. Yes, but the radiation is emitted by the atom. Then what happens is, if we know the frequency, because this radiation belongs to the electromagnetic spectrum, we know the speed of the light for any radiation of the electromagnetic spectrum is 3 × 10⁸ meters per second. And if we know the frequency, we can calculate the wavelength. Then using the wavelength or even the frequency, we can identify what kind of radiation was emitted by the atom. For example, if the electron moves from the orbit, in case of the hydrogen, from number 6 to number 2, then this emits this frequency, and this frequency corresponds to the violet. And if we calculate the wavelength, this corresponds to the violet. And the same happens with when the electron moves from number 5 to number 2, the frequency also corresponds to the violet, and this is the frequency, and this is the wavelength. And the same for the other case, from 4 to 2 is blue-green, and from 3 to 2 is red. Then let's try to do some math using this information we had here to solve the problem, using these equations. Yes, using this equation to calculate some of this radiation. And let's see, we will move. Then these are the this is the spectral lines. Yes, all these are the spectral lines of the hydrogen. Yes, this is how we can calculate, how we know what should be the lines in the, what should be the color in the line spectra of the hydrogen. And let's now try to solve this problem. We had an electron in a hydrogen's atoms jump from the excited energy level n equal 2 to n equal 4 to n equal 2. Then what is the frequency of the emitted photon? And we want to calculate also what is the wavelength of the photon. Then is 4 to 2, yes, 4 to 2. What we expected in our answer is some frequency around this value, yes, and this corresponds to blue-green line, yes. Then we expected something like that, and this is the line we want to calculate, yes, we want this line. This is the line we are going to calculate. Let's do the math. Then the first thing we need to know, and you will have, because you will have all these values, you will know all these values. Then the first thing we need to calculate what is the energy that corresponds to n equal 4 and the energy for n equal 2. Then how we will calculate this one? We will use this equation. And we know that N1 equals to negative 2.18 10 to the power minus 18 joules in case of the hydrogen, as this is the energy for the first level. Then let's calculate the energy for n equal 2 and n equal 4. And for n equal 2, and this equal to, if we use this equation, yes, if we use this equation, this one, we will have n equal 1 divided by, that in this case n, you see this n is 2 to the second. Means we had negative 2.18 10 to the power minus 18 joules divided by 2 to the second is 4. And that energy equals, if we divide, will be negative 5, let me write better, negative 5.45, negative 5.45 10 to the power minus 19 joules. This is a 4. And we will do the same to calculate the energy for the energy for the 4 energy level. And we use the same equation, we divide this energy divided by 4, because it's for the 4 levels, to the second. Then negative 2.18 10 to the power minus 18 joules, here is 0, divided by 4 to the second is 16. If we divide these two values, you will get negative 1.36 10 to the power minus 19 joules. And let's now calculate. Now we need to calculate the frequency. And to the frequency, we will apply this equation. We need to find the difference between the energy, the high, this is the high, here, this will be the high level, this will be the low level. And we need to get the difference between the high energy minus the low energy, and this must be equal to the h times frequency. And in other words, let's see where I can write this one, is we had here n equal 4, n equal 2, yes. Then the electron is here, and the electron jump from here to here. These electrons emit some radiation, then that radiation, then to this radiation we want to calculate the frequency and the wavelength. And in the experiment you are going to do, you will be able to see that radiation, yes? You will see a video and you will be able to see that radiation, yes? Because it's that radiation is in the visible range. And we want first to calculate the frequency. Then to calculate the frequency, we will use this equation. And let's now, I will write here the equation, probably will be better. And this is the energy. In our case, will be 4 minus 2, but 4 is minus 1.3619 joules minus, and here we had to be careful because we had the negative is from the equation, you see, but we had this number is also negative. Then we had to be careful with this sign here. Equals. Let's do this difference and then we will write the H value. Then negative times negative, then this is positive. Then it's this one minus this one. If we use to subtract these two numbers, just be careful, here is positive. Yes, negative times negative is positive. Then it's minus 1.36 10 to the power minus 19 plus 5.45 10 to the power minus 19. And we subtract these two numbers, we will get 4.10 to the power minus 19 equals. Let's write the constant. Plant constant is 6 point, is the H value 6.63 10 to the power minus 34 joules per second times the frequency. Yes, this is the frequency. Now if we want to solve this equation, we divide by 34. We divide by H value on both sides. And we divide the same. We will do the same here. Here is joules and here is joules per second. Yes, don't forget the units. Here is joules per second also. And this cancel out, and if we divide these two numbers, if you divide the numbers, you will get 0.617, and if we subtract the exponents, it's minus 19 minus 34. Then really what we had is minus 19 plus 34, and then you will have 10 to the power 15. If we want, and we had 1 over second, yes, because joules cancel out. You see, second is in the denominator, and this one equals to the frequency. If we want to write this one in scientific notation, we move to the right. If we move to the right, remember we subtract. And finally, we had 6.117 10 to the power 14. Yes, because we moved one place, one decimal place, and we subtract 1. 1 over second we know is hertz. And we know the visible. If it's in the visible range, the frequency must be 14, yes, if the number is in scientific notation. And now we calculate the frequency of that radiation. Then to know the color, yes, we can see is that frequency for what color correspond, and is here. Yes, it's close to 6.2. Yes, if we just write into the significant digits, this is correspond to blue-green color, correspond to this color, that frequency. To calculate the wavelength, again, because we know this is a visible range and the visible light belong to the electromagnetic spectrum, then we can use this equation. And we know the speed of the light there is about this value. Yes. Then we know the speed of the light, we know the frequency, then we can calculate the wavelength. As we divide by the frequency on both sides. And let me write this one here like that. And this value equals to 3.10 10 to the power 8 meters per second divided by the frequency, but the frequency is 6.10 to the power 14. And here, let me write 1/second because we need to cancel out the ionics. We need to see the ionics. If we divide these two numbers, we will get 0.486, and if we is 8 minus 14, we will get 10 to the power minus 6. Yes, 8 minus 14. The 1/second that cancel out, and we had the final answer in meters. Is the units we expected because it's the wavelength. Now, if we want to write this one in scientific, or let's write this one in nanometers. We know nanometers is 10 to the power minus 9. And to express this one in nanometers, what we can do is we move the decimal place 1, 2, 3. Because we move to the right, we subtract 3, yes? And minus 3 and minus 6 is minus 9. And we can write this one like 86 10 to the power minus 9 meters. But we know minus 9 means nanometers. Then we can finally write this one is 4086 nanometers. It's usually because there are small values we can express in nanometers, but this answer is right. Right? This answer, if you need to calculate the wavelength, yes, I did that extra steps to show you this wavelength correspond to this one. Yes, it's close enough. The value is close. It's 484 here, and we had 486, and it's close enough. And this correspond to the blue-green line of the hydrogen emission lines. Yes, that correspond. And this is how we can calculate the lines. Yes, we calculate just for one line. The next thing we want to discuss is the electron configuration. Now we know the electrons can be distributed in orbits. Then now we want to study how is the distribution of the electrons in orbits of an atom. And we want to study how we can distribute these electrons in the orbit. This is what we want to study in the next slide. Before to study, we want to study the quantum numbers, and this quantum number, because that are related at the energies, the energy states of an electron. And all these numbers are related to the energy of the electron. Then the first quantum number is the principal quantum number, and is we already discussed that, is the main orbits equals 1 and equal 2, 3 is the number of the orbit. Yes, 1, 2, 3. This is the principal quantum number. The angular momentum quantum number, which is represented by L, that represent the subshells. You remember the Schrödinger, he found that each orbit is divided in subshells. Then this angular momentum quantum number is represent that subshells of the orbit. Then that subshells can be S, P, D, F, G, H, can be any of this one. And these are how are the shape of these orbits. Yes. If there is the S, will be like that. Yes. If there is P, will be like that. Yes. And if it's D, it's complex. I will show you how it looks like the D orbital. Then more if the subshells can hold more electrons, more complex is the shape of the orbital. the magnetic quantum number is related to the orientation of the orbit. Here we had one example, this is the p orbit, the p orbital, and here we had, this is in x direction, this orbit is in y direction, and here is in z direction. And this is px, py, pc, is the orientation of the orbit. And a spin quantum number is the electron spin orientation. Yes, it depends how the electron is spinning. Yes, spinning up or spinning down. But in this course, we will going to concentrate in the first two quantum numbers. We will concentrate in the principal quantum number, which is describes the main orbits, and the angular momentum quantum number, which describes the subshells. This is what we are going to concentrate. Then here is just a summary. The principal quantum number is related to the distance from the nucleus. The angular quantum number is related to the shape of the orbital. And the m number is the magnetic, is the orientation, is the space. Yes, this is x, y, z. And the electron spin is the s number, is related to the spin of the electron. Then again, we will concentrate in the first two. Yes, I want to show how complex is the shapes of the orbits. Then in case of the orbital S orbital, this can hold just 2 electrons. See, this can hold just 2 electrons, and this is the shape. The p orbitals, this can hold 6 electrons, and each lobe, you see, each Paros lobe can hold 2 electrons. Then 2, 4, 6 electrons. The d orbital can hold 10 electrons, and is really complex. Is that this d orbital has 5 lobes, and each lobe can hold 2 electrons. Then 5 times 2 is 10. Then the maximum electrons the d orbital can hold is 10 electrons. Then the s orbital can hold 2 electrons. The p orbitals can hold 6 electrons. The d orbitals can hold 10 electrons. And you can see it's really hard to study the motion of the electron in this kind of space. It's complicated. And here we summarize what are the main energy levels, what are the subshell energy levels for each main energy, and what are the maximum number of electrons that shells can hold. Then in this case, we had the first orbit, yes, and this can hold just 2 electrons. This is one, they had 1 subshell, yes, 1 subshell. The second orbit has 2 subshells, S, P, and this can hold maximum 8 electrons, because remember, P can hold 6, S can hold 2, then 6 plus 2 equals 8. Then the third energy level has 3 subshells. Remember Schrodinger, what Schrodinger found. This has 3 subshells, S, P, D. S can hold 2, P 6, D 10. You add all of them for the third level of energy, we had 18. For n equal 4 subshells, S, P, D, F. S can hold 2, P 6, D 10, F 14. This can hold, if we add these numbers together, can hold 32. Then the first energy level can hold 2, the second can hold 8, the third 18, and the last one is not the last one, but the n equal 4 is 32. And what I want to here is just to make some picture to explain this, to explain these numbers. This is the nucleus. This is the first, this n equal 1. And this has just one subshell, is S. Yes. And this can hold maximum 2 electrons. Yes, maximum 2 electrons. The next subshell, the next is n equal to, let me smaller, better. N equal to, but remember n equal to has two subshells, SP. Then here we need to another subshell. Then this is the second energy level, n equal to, but this has two subshells, SP. S can hold maximum 2 electrons, P can hold maximum 6 electrons. Then 2 plus 6 is 8. This is why the n equal to can hold maximum 2 electrons. Now for the n equal 3, then we will have something like this is n equal 3. Let me write here. But n equal 3 has 3 different subshells, S, P, D. Then S, P, all this one correspond to n equal 3. All of this, yes. Then this is S, let me write here, S, P, D. 2 electrons, 6 electrons, D, 10. Let me write here the numbers. S, always 2 electrons can hold. P, 6 electrons. D, 10 electrons. And F, 14 electrons. And here we had 2 plus 6 plus 10, 18. And let's write here n equal 4, but I will just do some portion because it's too big. 2, 3, 4. This corresponds to n equal 4 because n equal 4 has 4 subshells. The subshells are S, P, D, F. S, P, D, F. Then if we add all of this one, we will have 32. Then n equal 4 can hold 32 electrons. Yes, it's 18 plus 14 will be 32 electrons. And this is important. Then what electron configuration is doing or is studying is how we can organize the electrons of the atom in this orbit. Yes, this is then how we can organize just in this way. Yes, just in this way. We have to follow this rule. For the first orbit, just 2 electrons. For the second, just 8 electrons. 2 in the S, 6 in the P subshell. For the n equal 3, we can just distribute the electrons, 2 in the S subshell, 6 in the P subshell, 10 in the D subshell. For n equal 4, for the fourth energy level, we can just distribute the electrons in this way. 2 for the S subshell, 6 for the P subshell, 10 for the D subshell, and 14 for the F subshell. And this is for S, for P, for D, for F, because belong to the n equal 4. This will be 3D, 3P, 3S. this will be 2p, sorry, 2s, 2p. And here we have just one s because we had one subshell. Then I hope this helped to understand the next thing we are going to do. And here we have the diagram of the periodic table because where the element is located in the periodic table is correlated with the electron configuration of that element. And one important thing we need to identify in the periodic table is the rows are related to the main orbital or the principal quantum number n. Then the first row is 1. The second row corresponds to the orbital number 2. The third corresponds to orbital number 3. For 4 row, we have to be careful. This corresponds to orbital 4, but for this part, it's not 4, it's 3, it's 4 minus 1, then correspond to orbital, to the third orbital. This row corresponds to the fifth orbital, to the orbital number 5, but here we have to be careful. It's not 4, it's not 5, it's 5 minus 1 is 4. And the same happened with number 6. Then this part is number 6, and here will be 5. This is 7, and this part will be 6. In the last group, in this block, then is n minus 2. And we will see why this is correlated to this one in the next slide. As then this one is no A, will be 6 minus 2 will be 4. This is no 9, is 7 minus 2, which is 5. Another thing I want you to identify is the groups. There is a block in the periodic table, and this corresponds to the subshells. And this block corresponds to the S block corresponds to the subshell S, and all the elements in this block, the last shell correspond to S. Is S subshell. Can be 1s, 2s, depend what orbit, but the subshell is always S. All the elements in this block, the last subshell is D. Can be 3D, 4D, 5D, depend in one row the element is located. All this group, the last shell correspond to the P block. And the same happen with these elements in this part. Always the subshell correspond to the F. One more thing is we can see the helium, which has 2 electrons, must be here. It's not here. But the reason is located in this group is because all the elements in this group, helium, the properties of the helium is similar to the properties the properties of the elements are in this group, in this column. Then this is why helium is here, but helium should be here. This is why helium is orange. Then now let's move. This is just, I want you to have some idea about this, about the correlation between the periodic table and the electronic configuration. Then as we say, then all these elements in the periodic table, the last shell must be S. Yes, must be S. Can be 1s, 2s, 3s, depend what is. Then we can say the last shell, for example, for calcium must be 4s. Yes, 4s. One more thing I want to, and this is the same happen with this group. The last shell must be D. This last shell must be P. The last shell must be F. One more thing, remember the maximum number of electrons each shell can hold. Yes? Then S, remember, I will want to write here, S can hold 2 electrons. Then you see S has 2 columns. Then if the element is in the first column, then this S will hold 1 electron. But if the element is in the second column, this subshell S will hold 2 electrons. This is why we had 2 columns, because the maximum electrons S subshell can hold is 2 electrons. Now let's go to P group. For P group, remember the maximum number of electrons can hold is 6 electrons. And you count here 1, 2, 3, 4, 5, 6. Then we know if the element is here, yes, then for example oxygen, then the last shell will be 2 because it's in this row, 2, P because it's in this group, and we count how many electrons in P, 1, 2, 3, 4 electrons, yes, then will be 2P4. We will do more examples of this one, but just I want to give some idea. But remember the maximum electrons P subshell can hold is 6. This is why here we have just 6 columns in this group. In case of D, the maximum electrons can hold is 10 electrons. And if you count here, you will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, this is why here we have 10 columns for D. In case of F, we had 14 electrons. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yes, and this is why we can, this can hold just 14 electrons. We had 14 columns here. Then let's move to the next. One more thing is important you identify in the periodic table. If this corresponds to the symbol of the element, will be carbon, correspond to C. The 6 corresponds to the atomic number. Yes, atomic number is the number of protons, but in neutral atom, the number of protons equals to the number of electrons. Then this is telling you how many protons and how many electrons if we have neutral atom, means same number of protons, same number of electrons, positive, same number of positive and negative charges. And again, this is the symbol, and here is the atomic mass. Yes, this is the atomic mass is in the bottom of, usually is in the bottom of the symbol. And these things also is important we can identify in the periodic table. I know in some books they use this matrix to get the electronic configuration of the elements or ions also, but in this class we are going to learn how to get the electronic configuration using the periodic table. And the reason is, if we understand how to get the electronic configuration using the periodic table, then we will understand also why it's important the order of where the element is located is important to know another characteristics of that particular element. For example, we will know how many electrons we had in the last shell if we know where the element is located. And this is to know that information is important when we are working or we are understanding the ionic bonding or the chemical reactions. And to know, for example, how many electrons in the last shell, how many electrons that element has in the last shell is important when we are working with ionic bonding or chemical reaction. Then I know in some books they use this method, but again we are going to learn how to use the periodic table to get the electronic configuration. Then let's start to get the electronic configuration using the periodic table for some elements. For example, let's start with hydrogen. And hydrogen, we know, has one, the atomic number is one proton, one electron. Yes. Then the hydrogen, one electron. Yes. And you see, this is the main orbital is 1 because it's in the first one. We will write this one 1. Let me write this one here is 1. It's in the S group, must be S. And it's in the first column. How many electrons? 1. Yes. If we want to represent this one, let me write this one here, get some space here. It's 1 is 1. And this is the, we will have something like that. This is n equal 1, 1 subshell. Remember, S can hold maximum 2 electrons, but hydrogen has just 1. Then this is the electron configuration for hydrogen, and this is how we can represent this one in a diagram. This is. Then let's try now helium. Remember, helium has 2 electrons. Helium must be here. Then this is here, but look, where the helium must be located is here in this position. Then helium, we can write here helium. We had 2 electrons. Then now, let's try to write the electronic configuration. Or maybe let's write first the diagram. As here we had helium. Here is the orbital. This is n equal 1. This is the S. S can hold maximum 2 electrons. That's 1, 2. Yes, 2. And let's try to get the electronic configuration using the periodic table. Then helium must be here. Then is 1 because this is the main quantum number of the principal orbital, 1. S, because it's in the second column, has 1, 2 electrons. Yes, 1, here is 2, and it's 2 electrons. And we can see here is 1 is the principal quantum number, is this one. S is the subshell. How many electrons? 2 subshells. Yes, 2 electrons in the subshell. And this is why the electronic configuration is 1s2. Let's try the next one is beryllium. And let's see, beryllium is here. How many electrons? 4 electrons. And let's try to do some diagram here. And for n equal 1, we had 1 subshell is 2. Maximum can hold 2. The next now is full. We can know this orbit cannot hold more than 2 electrons. And let's move to the next. Be n equal 2, and this will be s. Yes, can be s and p, but we need just s can hold 2, then it's 2 electrons. And we had 4, then we don't need to. We don't need to draw any other subshell. We had 1, 2, 3, 4. This is all the electrons. And now let's try to write the electronic configuration using the periodic table and compare with this graph we had here, with this diagram. And here is beryllium, yes. And if the beryllium is in this position, means the other shells, yes, before this one must be completed, must be full. And we start from here, then all these shells must be full, must be completed. Then it's 1, S, 2 is the first one, is 1 is the group S, 2, 1, 2 is 2, Then let's write here is 1 S2. Now move to the next subshell 2, because it's in the second row 2. Sorry, it's 2S 2S because it's in the group S, and it's 1 2 is in the second column. Then this must be 2, and this 2 plus 2 is 4 electrons. Let's try to compare this one with our diagram. We had 1 because it's n equal 1, S 2 electrons. S is this one. The second 2 is in the S shell, 2 electrons. 2S 2. Then now let's try with oxygen. Oxygen is here. How many electrons? 8 electrons. And oxygen, 8 electrons. Let's try to do the diagram for oxygen. Here we need to do a small. And this is n equal 1. This is a shell S 1. Let me write here. Get some space here. This is n equal 1. 1, 2 electrons. This is shell S. Now S is full, then we need to move to the next level of energy, n equal 2. And n equal 2. But here n equal 2 has two subshells, S and P. Let's draw here the P subshell. Yes. And this is S, this is P. How many electrons in S? Sorry, this is S and this is P. This one again. And this is S. This one is P. How many electrons in S? 1, 2. How many electrons in P? We had already 4. Then we need A, we need to, okay, another 4 electrons. 1, 2, 3, 4 electrons. Now we had 8. Yes, 2, 4 plus 4 is 8. See, this corresponds to the first orbit, n equal 1. These two subshells correspond to the second orbit. And now let's try to write the electronic configuration using the periodic table and compare with this diagram we had here. Then here is the oxygen. The other shells must be completed. Yes, the other shells, this is the last shell, and the other shells, if the last electrons are in this shell, the other shells must be completed. And here, and we start from here, and we will stop here in oxygen. Then this 1s2, yes, this shell is 1s2, this one is completed. Move to the next one. 2s2 is 2 S group, 2 columns is 2s2, is completed. Oxygen. But here in this case we had 2 because it's in this row 2, and we had P. This is the P group. Now because oxygen is in the 4th position, 1, 2, 3, 4, and we will write here 4. How many electrons? 2, 4 plus 4 is 8. Then it's right. Now I want you to compare this one with this one. Yes, it is 1s 2 electrons. Is this part. Yes. This is 2 because this is, remember, this is the subshell for 2. 2s 2 electrons. Is this one. 2p 1, 2, 3, 4. 2p4. And this is why we can describe the distribution of the electrons using this notation, yes, using this, because this explains this diagram we had here. But it's easier to do this diagram if we had 1, 2, 4, but if we had 100 electrons, it's really complicated, and it's easier just to write the electron configuration using this notation than doing the diagram. It's complicated if you had many electrons. Let's do the last one, in which we are going to graph both. Then let's, for neon, and neon is in this group. How many electrons? We have 10 electrons. Neon. Let's try to do the diagram here. This is the nucleus, then N equal 1. This is S, 2 electrons. It's full. We can know its maximum can hold 2. Then we need to move to the next orbit, N equal 2. And we know N equal 2 has 2 subshells, S and P. And this corresponds to N equal 2. This is S. Sorry, this is S, this is P. S maximum 2, P maximum 6, but we need 10. We had 2, 4, then it's okay. We can, it's maximum 6, and we need 6. We need to distribute 6 more electrons. 2, 4, 5, 6. Yes. Then now we had 10 electrons. 2, 4, and 6. We had now 10 electrons. And this will be the diagram for neon. Let's try to get the electronic configuration using the periodic table. Here is the neon, then the other shells. When I say the other shells, these shells, this must be full. And we start from here and we will stop in neon. And this shell must be full. Maybe 1 is 2. 1 is 2. The next is 2 is 2. The next is 2 because it's in this slot 2. This is group P, block P, and it's 2P. And we count how many is in this position. We count 1, 2, 3, 4, 5, 6. Now 4 plus 6 is 10 electrons. Then it's right. Yes. And now let's correlate this to the diagram and the electronic configuration using this notation. Then it's 1s, 2 electron represent this. Yes, this represent this part. 2s2, this is the 2 s 1, 2 electrons. Yes. Then this represent this subshell for n equal 2. This is n2, but it's p. Then n equal to p, 6 electron in this subshell. Yes. 2p, 6. Then I did this the electron configuration for few electrons in both ways. Just you can understand what is the meaning of each of these numbers and letters and exponents, if we want to say exponents, in this notation. Yes, is now you understand what is the meaning of 1, what is the meaning of x, and what is the meaning of these 2 is here. Yes. And now we are going to get the electronic configuration for some elements just using the periodic table. I want you just to remember is the S subshell can hold 2 electrons, the P can hold 6 electrons, D can hold 10 electrons, and F 14 electrons. And let's start with magnesium. And the number of electrons is 12. Yes, it's just here. And we say if the magnesium is located here is because the other the other shells must be completed. Then in this case, we start from here and we will stop here. Then it's 1s2 is completed. It's 1s2 because it can hold maximum 2 electrons. Then it's 1s2. The next is 2s2. The next shell is 2s2. We move to the right, then will be 2. Yes, let's follow also the n. This 2p6 is completed. Then move to the next 3s, because it's in the second column, it must be 2. Then now we can check. We had 12 electrons. If we add the number of the electrons, we had 4 plus 6 is 10 plus 2 is 12 electrons. And this is the electron configuration for the magnesium. Let's do now for phosphorus. Phosphorus, we had 15 electrons and is located here. Then let's try to write the electron configuration. Then the other shells are completed. Let's start here. Is 1s2 is completed. Move to the next is 2s2 is also completed. Move to the right is 2p6 is completed also. Move to the next, 3s2 also is completed. Move to the right. Then we had here 3p because it's in the P group, P block, 3p, and we count 1, 2, 3. And you can add the number of electrons. You had 4, 10, 12, 15 electrons. This is the electron configuration for phosphorus. Let's do now the electron configuration for chlorine. Chlorine is 17 electrons. And we will do the same thing, the same procedure. Then let's start here. The other shells must be full. Then it's 1s2, 2s2, 2p6, move to the next, is 3s2, move to the right, 3p, and we need to count where is 1, 2, 3, 4, 5. And if we add the electrons, we will get 17, 17 electrons. And this is the electron configuration for chlorine. Let's try for argon. For argon, we had 18 electrons. And we will do the same. Yes, we start from here. Will be 1s2, 2s2, 2s2, 2p6 is completed. Move to down will be 3s2. Move to the right will be 3p, and we had to count 1, 2, 3, 4, 5, 6. And if we add the electrons, we should get 18 electrons. And this is the electron configuration for this, for that elements. Let's try a few more just to practice. And let's try now calcium. Calcium has 20 electrons. Then we have calcium here, 20 electrons. And we will do the same thing as the other shells must be completed. It's here, we start here 1s2, 2s2, here, move to the right, 2p6, move down, 3s2, move to the right with 3p, and it's full, it's 6, yes, 3p6, all is completed, move down, will be 4s2. 4s2. And if you add the electrons, the number of electrons must be 20 electrons, and it's 20. Then this is the electron configuration for calcium. Then let's try it for arsenate. Arsenate is arsenate is 33. Yes, let's try it for the. Let me do one before to do arsenate. Let's do it for titanium. Is 22 electrons, and I will do on this because I want to explain something with this result. And let's do for titanium here. Has 22 electrons. Then for titanium, what we can get for titanium is we start from here, will be 1s2, electron configuration will be 1s2, move down 2s2, is full, move to the right, 3p6 is full, yes, and 3p6, move down, then we are, here it's not 3, it's 2p6, so 2p6, yes, 2p6, move down 3s2, move to the right, here 3p6, 3p6, move down 4s2 because it's full. Now here we had to be careful because here is the group D, but the group D we need to subtract 1 for the principal orbital. Then here is 4, but for D is not 4, it's 4 minus 1. Then 4 minus 1 is 3. Then will be 3D, because it's in the second column of D, this 1, 2, there will be 3D2. Again, because titanium is in the group D, for group D to get the main orbital, means this numbers, n number, you had to subtract this number, n is 4 minus 1. Then 4 minus 1 is 3, then it's 3D because it's in the group D, and 2 electrons because it's in the second column. Then here will be 3D2. Okay, 3D2. And this is the electron configuration for titanium. Then just I did this one first because I want you to notice this, how we can get the number of the main orbital for D. Yes. Then remember we need to subtract 1. Then this is the electron configuration for titanium. Then let's go back here. Now we did for calcium, then let's try it for arsenic. Arsenic is 33 is here. Is this one. Then let's try it for arsenic. Then we will have the same thing. Will be 1s2, 2s2, 2p6. Yes, we are here. 2p6, 3s2, 3p6. Down will be 4s2. Let me write here 4s2. Then here is not 4. Yes, it's 4 minus 1 is 3D10 because it's completed. Yes, it's completed. Then it's 3D. Remember, 10 is maximum 3 electrons. 3D10. For P is N. Then for P is 4. Then it's 4P. P, and let's 1, 2, 3. Then P. 3. Yes, this is the arsenic. Then this is the electron configuration for arsenic. Let's do for bromine. Bromine is 35 electrons. Okay. And let's quickly complete for bromine. For bromine is here, the other shells are completed. Then we will write here 1s2, 2s2. Yes, the second let's move to the right will be 2p6. Here then will be 3s2. And will be 3p6. Then will be 3p6 will be 4s2. 4s2 here. Then we need to pass through this one. Then will be 3d10. Remember, we need to subtract 1. Then finally here we had 4p, and we need to count. It's 1, 2, 3, 4, 5. And here will be 5. The last we want to do here is krypton. Krypton has 36 electrons. The last shell, and has 36 electrons. And now we need to write the electron configuration for the 36 electrons. And we will do exactly the same. We'll start here. It will be 1s2. And I will do this one. 2s2. 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Yes, it's 3d10, and it's here. Then the last will be 4p6. And what I want to notice in this, if we compare this, you see magnesium and calcium, they belong to the same column in the periodic table, magnesium and calcium. And this is the last shell. How many electrons? 2. How many electrons? 2 electrons. Yes, this is the last. It's 3s, 2 electrons, 2 electrons. And this is in the second column. It's in the second column. Then all the electrons, all the elements in this column, they had 2 electrons in the last shell. Yes, in the last shell, they had 2 electrons in the same way we found for magnesium and for calcium. Then this group, they had, and this is important when we studied ionic bonding and chemical reaction. And to know this has 2, I will write here just 2 electrons, but you know it's 2 electrons in the last shell. All the elements in this group. Let's try it, for example, for this group, phosphorus. Yes, phosphorus. Then let's see, we did for phosphorus and arsenic. Let's see how many electrons in the last shell. How many electrons we had in the last shell? We had 3 electrons. And we had 3 electrons. Sorry, we had here 5 electrons. Yes, 3 is the last shell. 2 plus 3 is 5. Here we had also, this is the last, is 4. The last shell is 4. 2 plus 3 is 5. And they had 5 electrons in the last shell. Yes, this group, all the elements in these columns, they had 5 electrons in the last shell. Then they had here 5 electrons in the last shell. Yes, 5 electrons in the last shell. And you see, if we focus, this is a little complex group. We will focus on this too. All the elements in this column, they had 1 electron in the last shell. All the elements in this column, they had 2 electrons in the last shell. All the elements in this column, 3 electrons in the last shell. All the elements in this column, 4 electrons in the last shell. All these elements, they had 5 electrons in the last shell. we didn't complete this one, but it's easy to see they had 6 electrons in the last shell, 7 electrons, and let's see what happened with the last group. You see, they had, this is the same level, 2 plus 6, they had 8 electrons. 8 electrons in the last shell, and we here, this is 4 and 4, 2 plus 6 is 8. Then this group, they had 8 electrons in the last shell. Again, this information is important when we are studying the ionic bonding or the chemical reactions. Then this is, I want you to understand how to get the electronic configuration using the periodic table, because we can understand another properties of the elements, okay, like this one. Yes. Then all remember the column for this group and this group is telling you how many electrons the elements had in the last shell. 1, 2, 3, 4, 5, 6, 7, 8 electrons in the last shell. Then when the electrons, they had huge number of electrons, it's good to use the condense or abbreviated electronic configuration. And let's do one example to know how we can write the electronic configuration using the condensed form. Then to write in condensed form, we need to use what always we will use as reference is this group. And this group is called the noble gases. And this group we use as reference because they are stable. When the electrons, they had 8 electrons in the last shell, they are very stable. They don't want to combine with any other element. As they are very stable, they don't need to combine with any other element to be stable. Then this is the noble gases, and this is we will use as reference to use to write the condensed electronic configuration. And let's write the electronic configuration for xenon and for baryon, for this and baryon, for these two, and then we will see how we can write the electronic configuration, the condensed in condensed way. And let's write here for xenon the electronic. This is as 54 electrons. And let's start here. This is 1s2. Next is 2s2. 2p6. Move down 3s2. Here 3p6. Down 4s2. Here we know is no 4 is 3d10. And we need to move here. Now it's again 4p6. Move down 5s2. Move to the right is no 5 is 4d10. Move to the right. Now it's again 5p, and it's 6 because it's the last one. Yes, we count is 6 position and 6. And this is the electron configuration for xenon. As you can see, using the 5 level, using the 5 and 5, 2 plus 6 is 8. Yes, 8 electrons in the last shell. Yes, it's 5, 5. Then now let's write for baryon. Then we know for baryon will be similar to the xenon. Yes, it's similar because it's just, here is xenon, and it's similar to the xenon. This part must be the same. Just we can try it, should be the same. Just we need to add this part. And it's 1s2, 2s2, 2p6, 3s2, 3p6, need to move 3p6, 4s2, 3d10, 4p6, yes, here, 5s2, 4d10, as is here, is 4d10. Now we need to move here, will be a 5p6, and now we need to add this part, 6s2, because it's in the second column. What we can see is the first part is exactly the same as the configuration of xenon, as the same. Then we can write just this one in this way. We replace all this part by this one. Then we can write the electron configuration. Just we use brackets, and then we write the other part, 6s. Then we can replace this by the xenon, but in brackets, and this represent this part is exactly the same as the configuration of xenon, and this plus 6x2. Then the only thing is when we write the condensed electronic configuration, we can use just the noble gases as reference. We need here only we can write the noble gases. Then in the assignments, you will have to do for some you have to write the electronic configuration for some elements that had a lot of electrons, and you can use the condensed electronic configuration notation. But in the test, you have to write the complete electronic configuration. Okay. Now we want to write the electronic configuration, the electron configuration for cerium. Cerium is 58, is the atomic number is 58, is here. Yes, this is cerium. And we need to be careful because here you see, here we have lanthanum is 57 and the next is not 58. Yes, 58 is just here. Then why they are grouping like that? The reason is all the elements in the group F, they had similar characteristics, similar properties. And this is why it's in this way. Then we need to be careful when we need to write the electron configuration, because we need to move from here to here. And let's write here what we had here. We want to write for cerium is here. Yes, let me write here cerium, and this is 58. And we had here, we had lanthanum, which is 57. Let me write here lanthanum, and it's 57. Yes. And this is why we need to jump. Then what we will do is the first part we will write the electron configuration in the way we learn, and we will just, when we reach here, we need to jump to here. Yes, we need to jump here. And let's now write the electronic configuration. For the first part, we know how to write that. This is cerium, has 58 electrons. And we start here is 1s2, yes, 2s2 is full. The next is 2p6 and it's full. The next is 3s2, is full. Next is 3p6, is full. 4s2. And remember, here is no 4. We need to subtract 4 minus 1 is 3. This is why we have here 3, 10. Move to the right, 4, p6. Move down, 5, s2, 4, d10. 10, 5p6, down 6s2, and now we need to write this one. Then lanthanum will be 5 because it's 6 minus 1 is 5. 5d, because it's in the first column, we need to move from the first column to here. Then we will write just 5d1. This is the, we need to move from here. Yes, this is 5d1. Now move down. This is f. What is the main number? Then is here is no 6. We need to subtract 2. Then it's 6 minus 2 is 4. This is why we had here 4. 4. Okay. Then it's not 6. It's 6. 6 minus 2 is 4. Then this is 4 f. And now because it's in the first column, will be 4f1. 4f1. Yes, remember we had here 14 columns. Yes, because the maximum electron in F are 14. This the maximum number of electrons is 14. And 4f1. And this is the electron configuration for cerium. And now let's move to the next. Here we want to write the electron configuration for hafnium. And let's see what is hafnium. Hafnium is here, is 72. Yes, it's 72. But you see, we need to jump here because the next is not 58. This is the same thing happened last time. We need to move here. We need to pass through all this one and then move up. And in the same way, we will write the electronic configuration. It is 57. Move here. Yes, pass through this one and move up. And let's try to do that. Yes. And we had here, let's write here again, this is 58. This is 57. And here we had hafnium, which is 72. Okay. And we had hafnium with 72, 57, 57, and 71 is here. Yes, I will write this one we had as reference. Yes, 71 is here. Then we want to write the electronic configuration for hafnium. And this is why we had these arrows. We had to, from here, we need to move down, pass through this one, and then we need to go back. Then let's write the electronic configuration until this point, and then we will do this part slowly. Then we know until this point. Then let's write here hafnium. We had 72 electrons. Let's start. And the other shells are completed. Then we had 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and we need to move to 3d10, 4p6, and 5s2, 4d10, 5p6, 6s2. Now, because we will go back to the group D, we will take care of the group D at the end because we need to move down and go back to the group D. Then let's do this first part. And we know this one is not 6, it must be 4 because it's 6 minus 2 is 4. Then 4F. Because we pass through all the group, then means this is full. Then will be 4F14. Now we go up to the group D, and here is not 6, it's 5. Yes, 5D. Because it's in the second column, will be 1, 2, will be 5d2. And this is the electron configuration for half mean. And just we need to be careful with this part of the periodic table when we are writing the electronic configuration for the elements in this group. Yes, for the elements after 57. Yes, where the atomic number is 57. One more thing I want to discuss is the electron configuration of the ions. Then what is the ions? Then we up to now what we discussed, the electron configuration of the neutral atoms is the atoms that have the same number of protons and the same number of electrons. Yes, this is what we can see, the atomic number corresponds to the number of electrons if the atom is neutral, if the number is in the periodic table. But in some cases, we have atoms that are negative charged. Then in this case, the atoms, they have more electrons than protons. In this case, anion is more electrons than protons, like in this example. Yes, more electrons than protons. Yes, we had 5 electrons and we had 3 protons. Or can be also positive charged. The atom can be positive charged. In this case, the atom has more protons than electrons. And in this case, the atom gains electrons, but in this case, the atom loses electrons. And this is why become a positive charge. There's more protons than electrons. And we want to learn how to write the electronic configuration for these elements. And in this case, we want to write the electron configuration for sulfur. And we will see, let me go maybe here. Sulfur is 16, is this one, yes, it's here. But sulfur is we had a ion of sulfur. Then if sulfur is the notation of the sulfur is something like that, yes, S with some negative number on top, yes, then what this means is this is an ion, and if negative means this atom gain 2 electrons. Yes. Then if sulfur is, if it's like that, it's neutral atom, but if the notation of the sulfur is like that, means the sulfur gain 2 electrons. Means they had more electrons than protons. How many more electrons? 2 electrons. Yes, this 2 means has 2 more electrons. And we need to be careful because when we had sulfur, we had 16 electrons, but if the ion of sulfur has 2 more electrons, then now the sulfur has 18 electrons. Then if we want to write the electronic configuration of this ion, we need to write the electronic configuration based on 18 electrons, not 16 electrons. Yes, because we want to write the electronic configuration for the ion. And the electronic configuration for this is 18, for this ion of sulfur is 18 electrons. Then let's write this one. Fortunately is, yes, sulfur, then all these shells are full and will be 16, then will be 1, 2, 3, 4. Yes, let's try 2. Go back here is 1 is 2, 2 is 2, then we go down, will be, we go to the right, will be 2p6, down will be 3 is 2, will be 3p, and here we need to count. 3p will be 1, 2, 3, 4. but it's not 16. We had 2 more. Yes, then we need to write here. Will be not 4, will be 2 more, will be 6. And it's 4, 10, 12, 18. Yes, this is right. But the electronic configuration for just for sulfur will be 1s2, 2s2, 2p6, 3s2, 3p4. Yes. But for the sulfur, for this ion of sulfur, then we need to add 2 more electrons. And this is the electron configuration for the ion. Now let's write the electronic configuration for the mercury. Then for mercury, what happens is pure neutral mercury is 80, is here. Yes. But if we had the ion of mercury, yes, is +1, means if it's positive means if it's positive ones means that the mercury lose 1 electron. Then the electrons for the ion of mercury is not 80, is 79. Then we need to write the electronic configuration accordingly. Yes, and in this case, we need to write the electronic configuration based on 79 electrons. Then I don't want to go back to this one, then I just will write the electronic configuration just for the ion because it's long one. Then here will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3b10, 4p6, 5s2, and I will move here with 4p10, 5p6, 6s2, 4f10, 5d, and if it's mercury, will be 5d10, but because it's the ion, we need to base it on this one, will be then 3d9 because it's like the configuration for 79. Yes, and here will be 5d9. Yes, this is the electron configuration for the ion of mercury. And the last thing I want to discuss is the concept of isoelectric ions or atoms. The isoelectric means ions or atoms that having the same number of electrons on the same electronic configuration. But now we know how to get where we can identify the number of electrons if we had even an ion or we had neutral element. And for chlorine, let's see, for chlorine, pure chlorine has 17 electrons. Yes, but we had -1 is charged negative, means gain 1 electron. Yes, because it's negative. Then if pure chlorine has 17 electrons, if we add one more, then this ion will have 18 electrons. Let me write here 18 electrons. That's why here pure chlorine has 17 electrons. And if it's negative charged, gain 1 electron, then it's 18 electrons. If it's positive charged, +1 means the chlorine lose 1 electron. It lose 1 electron, then this ion, this positive ion of chlorine will have 16 electrons. 17 minus 1, 16 electrons. And what we can say is this the ions are not isoelectric. The reason is they had different number of electrons. Then we can say here, they are not isoelectric. And let's try the next problem. We had the ion of bromine, and let's see bromine, how many electrons. Bromine is 35. It's 35 because the atomic number is 35. Then the pure bromine has, let me write here, pure bromine has 35 electrons. Because it's -1, the ion is -1, means gain 1 electron. Because gain 1 electron, then this ion of bromine will have 36 electrons. In this case, we had krypton is not an ion because it doesn't have any positive or negative number on top. Then this is just neutral. Then just we need to check krypton is 36. And here krypton is 36 electrons. And because they had the same number of electrons, we can say yes, they are isoelectric. Okay, this is all I had to discuss for today.